vamos a recuperar ya el trabajo que hemos.
Let us use some of the things we did this morning. I think it's now a good time to recover that network model that we had generated prior to starting the exercise. We need to adjust these settings. Those who start from scratch, I'm going to go through the steps quickly. You open a view. We will first load the cartography, exercise data, city topography, urban topography. I have 23031. This is the projection system. We will group by layers. We will name this topography. We loaded topography. Very well then. As for the network, since this morning we worked around node ini, arc ini as initial, we will load the arc and node layers, but we're gonna use arco and nodo, the ones we had in the support folder. We group these. We'll call it saneamiento, sewage system. Let us use symbols. We set the color, blue, properties, arrow, decoration. One arrow. Fine, we have single arrows. Let's go to nodo, choose any old color. Fantastic. We have our project. Let's zoom in. Okay, you all ready? This is our project right where we left it this morning, with the arc and node layers full of information. Let us look at the node attribute layer. This is all the data. The arc attribute table, here it is. It's full of information. I take it we're all on the same page. Okay, we've seen the theory. Now let's move on to the practical side of the hydraulic system. We only have 45 minutes, so this is just going to be a quick snapshot. As I mentioned earlier, designing the drainage subcatchments can be done manually or using geoprocesses. We go to the menu View, Vista, Geoprocesses Manager, Analysis, Computational Analysis. You need to reach this point here. You need to get there. Geoprocessor Manager, Analysis, Computational Intelligence. Jose Luis, are people following? Super. We opened the geoprocess. As I mentioned earlier, this geoprocess uses some nodes which will generate concentric polygons. Nodes will be the entry or layer, or the input layer. Do you want Delanois triangles or TSN polygons? Triangulation is the first step. It's a triangle among nodes based on the optimal distance principle, and after we have this triangle, using the central point of each triangle, we generate a perpendicular line, thereby generating polygons. So we're going to mark Thiessen polygons, and down here we say incremental tin based on Hall triangle or involving triangle, and output layer would be Thiessen underscore initial. Okay, datos de ejercicio, exercise data, models. We've been working around management. We're going to change folder and going to move on to modeling. It says modelado in Spanish. And there's an empty folder. We will name it Thiessen underscore inicial. We save. And we will now proceed as follows. Apparently the geo process has been completed, and we have a triangle mesh. We have polygons. We deactivate and use a livelier color, or a color that stands out more. We have attained via a node layer through Thiessen polygon methodology to generate polygons that are concentric to our nodes, which are a hydrologic simplification, but enough to proceed and make headway. Are we all on the same page? Super. The next process would be setting the outer boundary. As good hydrologic engineers, we would have to design the outer perimeter, and we would cut the polygon. We will not draw the polygon because we don't have time, so we're just going to load the data. So we go back to agregar capa, add layer, modelado de drenaje urbano, modeling of urban sewage system, and inside the folder called originales, originals, we load the internal perimeter layer, perímetro interno in Spanish. This layer is a drawing that we have produced, being excellent engineers as we are, and we get the internal perimeter. So we just need to establish this outer perimeter. I have a cheat sheet here. We go to Tools, Polygon Layers in Sextant, and we select the following option, intersection. Okay, Sextant, Tools for Polygon Layers, intersection. We need to establish two layers. The first would be Thiessen initial. The second would be inner perimeter. The name of the profiled vectorial layer, and This is the name we're going to use, and we will use the same name for this. We will use the same name, so this will be called TSN recortado, or profiled TSN. We save and run. As a result, we have a new Polygon layer, which are the profiled TSN. We can deactivate the initial TSN and the internal perimeter. And we have the Polygon layer, which if we make transparent and use a lighter, thicker color, we will have all the information. Okay. If we open the attribute table of this layer, we only have some autonumerics that have been automatically generated by the software. Now we need to move from this single column table that is quite useless. We need to go from this model to a comprehensive hydrologic model. Since we don't have much time, and I don't think you are too interested in it, let me show you the completed hydrology layer and play around with it. So once we get here, we use the table editor to enter new fields and perform the calculations. And we would reach this point here, the subcatchment layer that's right there in the support folder. So again, modelaje urbano, and we click on the subcatchment layer file. The subcatchment layer would be the same TSN that we had so far, but with a specificity, which is that we have included two areas outside the system which constitute inflow to our urban network. So manually, we've added these two areas. We've done this manually, but we have softwares that allow for an automatic generation. But for such a small basin, we can do this manually quite fast. So we have the geometry of the two external inflow basins and the geometry of the internal inflows. So we can deactivate the initial TSN perimeter layers because the geometry is already in subcatchment. And if we open the attribute table, you see that we had an attribute table that was not very useful, and now we have this other table with all this information. So very easily we have been able to fill in the different fields. We can see how these fields are produced if you want to. This initial node can be done through a spatial link. As for the basin ID, this is linked to that of the node, and change N for S, replace N for S with the superstring of the field calculators. It's easy to do. Also, the assigned rain gauge. We have the information here. Area in hectares. We can use the field calculator or a geometric function, but be careful that we're dealing with hectares here to divide by 10,000 to obtain square meters. The imperviousness coefficient, so what amount of each micro subcatchment is pervious and how much is pervious and impervious. You can look into the perviousness of each subcatchment. By default, we have 90% here, but there are certain areas, greener areas, gardens, parks, that might be more impervious. This parameter might change, and our model is extremely sensitive to this parameter here. As for width, it studies each the width of each basin. It takes some time. This can be attained by geometry matching using perimeters, areas, and otherwise you can calculate this manually. An interesting geoprocess would the intermediate average slope. This is really, really interesting. So if we have a topography, some level curves, with a sextant, this topography can be converted to an elevation raster. With sextant, again, this elevation raster can be converted to a slope raster, and the latter can then, through polygon grid statistics, this parameter, we can determine the average value of this raster per subcatchment. This is the way we've obtained this value. If we have time, we'll see this in greater detail afterwards. This is to attain an average slope of our basin. As for maining coefficient for impermeable, 0.13, for pervious, 0.25. Here we could apply this formula, which on the basis of the average slope, we have the first amount of water that is not ran off. Here the value is 0, 0 again. As for flow typology, there are three options: pervious, impervious, from impervious to impervious, or both separately, from permeable to pervious. And length, since the deposit model is supposedly rectangular, this is almost automatic. Let me see. The software is processing. Okay. Edit. We start with the easy part. Length, since it's a rectangular deposit model, and we have the average width of each subcatchment. The length can be calculated as easily as dividing the field area in hectares by the width, and since the area is in hectares, obviously this value here needs to be multiplied by 10,000, thereby obtaining the length value. This is an easy calculation. We can be a little bit more daring and, for instance, try to do this other geo process, which is the average slope in each subcatchment. To do so, we need the slope raster. So first, let's close the table for now and load the slope raster. We select the driver for rasters. We click on the originals folder, and we have elevation maps, slope maps, and infiltration maps. Explaining this in detail would take very long, but you can use the sextant, fill in the blanks. It's possible to have a digital elevations model. Let us simply load the slopes. Once you have elevations is ready, we load this, and this is the outcome. It's a raster filled with values, and with this slope raster, we simply need to perform this gvSIG geoprocess, which is tools and layers for polygons, grid statistics in polygons. It requests a raster, a slope raster. We only have one. It requests a polygon layer. We'll just say subcatch. And as for the output, we will choose datos de ejercicio, exercise data, modelado de drenaje urbano, and we will name this file subcatch underscore pend, as in pendiente, slope in Spanish. This is just for you to see how gvSIG works. We save and then click OK, aceptar. This geoprocess, I will repeat this because I hear some mumbling in the room. This is a geoprocess under sextante, tools for polygon layers. It's called something like statistical analysis, tools for, I can't remember, says the speaker. And we go to Polygon Grid Statistics. This is a geoprocess that requests the output raster and the polygon layers. We are requested to save this. We'll save it in the directory we're working right now. We click OK, and this generates a new shape. Let's gain some more insight. We open the addition table, and 4 new fields have been generated. We have the average, variance, minimum, and maximum. For each subcatchment, we have the average slope, the variance of the latter, the minimum and maximum slopes. If we check the this field, the slope average, we will get the average slope here. For the hydrologic process. Let's repeat this process because it's highly interesting. As regards infiltration, we can now load the infiltration raster, which is Z3NCSES in the same folder in originals. And this is quite easy. It has its know-how. This is uses the methodology of the Soil Conservation Service that had been adapted by the Catalonian Water Agency using a slope map with a 3% level with the land use map that has been reclassified by the values in the Soil Conservation Center. We perform a double intersection. We perform a first intersection between two and then go for a double intersection. And I've said this very, very quickly. Those of you who are familiar with this language will have understood this quickly. You have this NC. We will repeat this process so as to determine the runoff coefficient and the average in each subcatchment. We will repeat this sextant operation. These values are interesting. So tools for Polygon layers, statistics, we intersect NC, and it doesn't matter if it's subcatchment. We can choose either of these. Doesn't really matter. Let's see, we'll try the last option, and then we include new value. Again, same folders, modelado, and this one will be called TSN. Well, no, subcatch, because we're doing the subcatch underscore NC, or the NC values. We save and run. This is when gvSIG decides to crash or not. It hasn't crashed. There's a cliche that it fails to perform the process, but that's generally not true. It's the user who doesn't do the right operations. Let's look at the table. We have 4 new columns with the statistics for NC. Obviously, we're interested in this column here, the average. This value is then exported onto a new table, that of NC impervious parameters. Since we only have 20 more minutes, we will not generate a table with these NC values. We won't generate tables either for anything else. We will finish with the hydrologic assessment, and we will use the last subcatchment, and let us remove some of these layers, or deselect these layers, and again, let's simply delete everything that do not help any longer. They've been really useful, but they're not anymore, and we just to keep the subcatchment. To make this view a bit lighter, we can remove the slope and NC maps. So this is a simplification. So transparency a bit thicker. There you go. Now all that's left is really, really simple. we need to perform another gvSIG geoprocess. It's quite simple, but we don't have time to complete that abstract vertex layer. This famous vertex layer is actually a layer whereby elements such as this arc here that goes from this node to this other node, but there's a curve, a bend. So you have 1, 2, 3, 4, 5 turning points that and we need to tell SWMM that these turning points are there so that it can all be calculated. We don't have time to do so, but this is calculated. So this turning curve points are identified, included in the model. Since we don't have much time, I have this data already recorded. Let's change the driver to shapefile support, and then the shapefile called Vertex, Vertice in Spanish, and let's pick another color, a darker one maybe. So you have these little dots. There's not that many, in all honesty, because this network is not very bendy or curvy. So it's a geoprocess by which you have the little vertices and turning points, and this is needed for SWMM to perform an accurate drawing. Otherwise, SWMM will say this arc goes from this node to this other node and would therefore draw a straight line. So this layer points out the little turning points. Everything is ready for the mathematical model then. If we check the arc layer, you will see that for the mathematical model, the information is there, all the data is there, and all of these are conduits. There are no flow regulators here. It's a tree-like, simple network. So it's perfectly ready. Then we would have to select the DBF, but that's easy to do. Then as for the node layer, we check the attribute table, and you see they're all junctions. In SWMM there has to be one that's out file, because you need an out file, an exit. You need to tell the mathematical model where the water is exiting the system. Here you don't have deposit or anything, you just have nodes and an out file. We'll work with a dynamic wave model, and if you recall the latter, remember that the nodes could not be dividers, so you can't have dividers here. Okay, so everything is ready. Prior to going to SWMM, as I mentioned, one of the advantages of working through gvSIG is that we can control all of SWMM parameters, all of these parameters from gvSIG. And this is good because you avoid data duplicity. Because if you go from SWMM to gvSIG, then from gvSIG you go back to SWMM, and then you don't save the information in gvSIG, you get duplicity. And to prevent this from happening, we have developed the communication extension so that any data you need for SWMM you can have in gvSIG. So any change you need to perform is easier to do from or in gvSIG rather than in SWMM. So you always do this to avoid the duplicity, but this is up to every engineer to decide. From gvSIG, you can control absolutely everything. So you just need to tell the gvSIG what to do. You can say run with the command with this initial file, this output file, so you can have all the data in gvSIG, thereby avoiding omissions and errors. So if this is so, let us see where are those, where's that piece of information. So prior to exporting, we have to check what other data needs to be checked. This can be done through DBFs that have already been prepared. So we use the table editor, and I can load the options table, project ID table, and the time series real and the ringage table. These 4 tables will allow me to control all the SWMM parameters and settings. I will control the project attributes and characteristics, the allocation of rain to rain gauge, and everything. So it's these tables are in the support folder, and you have to click on these 4 tables. We open them, we load them, and in just a few minutes we can see all of this information. Let's start with the options table. Here we have the different SWMM calculation settings or parameters, and it will say for each work unit will be CMS, cubic meter per second, because if we say gallons per inch, it will take our SIG measures with the units that are not the international standards. So we have use the metric system, and this is very, very important. Then as for infiltration model, I mentioned this earlier, we will use we have to say this curve underscore something number. I forgot to mention that in the handout you have this DBF, which furthermore is attached to the software. If you click on help, ayuda, you can always click on help. It's actually thinking, not helping much. This DBF here, apart from having it in the instructions, is in the guide. So you have a little handout, a little guide explaining details, and tells you about the communication, how this is installed in the extensions directory, and the use. And it very briefly mentions how the subcatchment vertexes layers are done.
And here you will see an image on the next sheet of the complete model, so that you know exactly where you are in the arc node and on the table that we have to work with for the different types of arcs and nodes. And then what you will find is a series, a list of DBFs with the different fields associated, and with the names that things should bear. Well, if you have any doubt, well, you can read that list of names, well, for each and everything. So it's quick help, it's very nice. If I don't know what name I should put here, I go to the support sheets and I will find the solution. So the table might even send me to the SWMM guide, but I mean, at the end, we will find the information. So it's always easy to find the parameters. The calculation factor type, dynamic wave flow, the starting date. For example, here we have theoretical days, the 1st of the 1st, 2001. And we have also the end date, the lasting time for the simulation, simulation every minute, for example, the frequency of the simulation, the calculation for the results are offered every second when we have rainfalls, or every 20 seconds with a dry situation, the pounding off, the pounding on. And if I say yes, well, the flow excess that are expelled by the nodes will be retained, and when the capacity allows it, well, it will be re-injected in the flow. So if it's lost and then rejected, well, obviously it is modifying the reality, and it is giving a fake value. So we have to take that into account. This is a theoretical model in order not to store anything in the nodes. And we have also this 1 second parameter that is required for this selection of the calculation method. So if SWMM is working with a dynamic workflow, with 1 minute, it will calculate more quickly, but the equation will not converge and the result will be catastrophic. And as engineer, we have to avoid that. From SWMM, we will be playing with the interface of SWMM. So with this table of equation, I will be able to control the different SWMM parameters in one single direction from SWMM to gvSIG. Here we have another table to get the information, basic information on the title, the author of the project. It's a very simple table. On the next one, I'm sharing with WMM, saying that on the rain gauge, well, it is assigned to a node with this volume format, with those intervals, with those coordinates. I really set up the rain gauge, and if we had more than one, this is the table that we would then use for their assignment. And here we have the rain table, in which the time series is rain. We have different volumes that are extracted according to the alternating methods, the alternating block system. So we have here analyzed the different control parameters, the hydrologic parameters, and now we have simply to set up the extension. All that information should be included in a very concrete directory. It is the support directory that we have prepared previously, and if we want to export it, well, we can do it. We have geometric parameters, pipes, and junctions. For EPA SWMM, we also need all the parameters. That option allows to draw in SWMM the different subcatchment. each subcatchment might have from 15 to 20 points. If we have 10,000 subcatchment in one city, obviously it might took, well, years for the export and import process. So we can, well, deactivate the icon for the design of subcatchment, and it will be much quicker. So here we indicate the directory where we will find all the shape and DBF, support DBF, and the support directory is where we will find all the support DBFs that have been prepared. We have here the exit, the output directory. We will set it up like this. And, well, we put the name, for example, Practica1.inp. We accept, we agree with that setting, we save it, and it has shown 105 subcatchment. We have the vertex, and we zoom out the desktop, we open the software, and then we go to SWMM. Let's wait for 30 seconds in order for you to open the software. I would like to thank Francisco Javier Martinez Solano for its effort together with his team at the Polytechnic University, because they have translated the 5.118 version from EPA SWMM into Spanish, but also the guide. And thanks to that translation work, the engineering world, not only in Spain but also in Latin America, has been able to enjoy that work and to understand that fantastic calculation method and implement it in their different societies. So thank you, Francisco Javier, for this amazing work. That translation into Spanish of EPA SWMM is opening right now. So we have only 5 minutes left to explain how the program is working. It's very intuitive. You can contact him. He is organizing different training here in Valencia. I don't know if he's organizing online training too. No, it's not the case. Well, sorry about that. Thank you. So you can play with it. We are going to load the general file, and we are going to visualize the software. We have only 5 minutes left. The file has been loaded. We open it. Let's find the file. It's Practica1 INP. It has to be loaded as we visualize it in gvSIG. Well, we can check some parameters. If we go to the subcatchment editor, well, we see the different parameters that we have loaded in gvSIG. If we check the nodes with the node editors, we see, well, the parameters that have been loaded in gvSIG. If we go to the calculation options, and in the general menu, we see the number of curves for the infiltration model and the dynamic wave model. And we see the frequency intervals that we have defined before. So it seems that the model is ready for calculation. So we are going to start the calculation. The simulation is starting. It is for a 1 hour rainfall. So we have an error margin that is quite acceptable. It seems that the calculation is quite positive. We can check in the report and the temporary evolution where we can choose one of those parameters, one of the system lines, to see a bit how it is working as far as flows are concerned now. In the 3-hour simulation, we see that there is a peak matching, well, the first 30 minutes. It's a very small basin, and the peak, the rain peak, matches the flow peak. We could generate more graphs like this, but it is showing us that the calculation is quite right. We should analyze it a bit further, but we don't have the time to do it. But it seems from far away that, well, the calculation is quite nicely done. We have the result in the menu report, situation report. And here we have, for example, a 10-year ago rainfall. It's only a virtual, and it's interesting to know, well, the behavior of such a rain for any village, for any city in Spain or in Catalonia. And the most interesting parameters that we might observe are the following. What is the node behavior when we have heavy rainfall, and the online parameter, and SWMM has a weakness. If we are expulsing flows in nodes, it is very important before doing any analysis to see what's happening in the flooded nodes, because if it's the case, I go to flooded nodes, and there I will get a list of at least 20 or 30 nodes that have been flooded. At the flooding time, we see that here one has been flooded during 1 hour, or others much less. We see here the matching parameters of the simulation and the volume of water that had been expelled. We see that it's like 10 to the 6 liter. And we see that we have lots of those nodes with less than 1 cubic meter. We see that, well, less than 1 cubic meter has been expelled from those nodes. We have also critical nodes. We have the node 24 with more than 1,000 cubic meter of flooding. Here we have the 5,000 for nodes 50. So you see, we have that information. It is the format that that is available. We have the information for node 34 or node 50, and I can check what's really happening with the flooded nodes. And well, unfortunately, we don't have more time to play with SWMM. But it allows us to do lots of other stuff, like, for example, different profiles, different longitudinal profile. I use, for example, the initial node, the final node. He designed the path we find the different longitudinal elements. I can also generate simulation on that same profile to see how it is being loaded with water or how it is being emptied. So the SWMM editors and the result views are very attractive. As an engineer, I might be interested not only in that, but also in being supplied with a real map of the situation. And so we, that's it. We have we have made it. We have come to the end, and so we also see the behavior of the maps here. But it is very interesting to read this result report and draw some conclusion on the screen, and very graphically. So with the simulation that we've done to make sure that we are saving this report, I have to save the result of the simulation. I say yes to saving those results, and in the same directory where I, well, you see, well, unfortunately, it has not been saved correctly. This is not the first time that it happened to me, so we are going to repeat the process. So from time to time, it's being saved, but from time to time, it's not being saved. So I'm loading Practica 1, and I save it with under another name. That might be the trick. So so I say I will name it Practica 2 now. And then I run off the simulation. I run the simulation, sorry, and now we have Practica DOS. And now let's have a look to see if it's being saved. I save it. I go to directory. I go to the data file. Now, yes, it does appear. We have Practica DOS. I'm going to delete Practica 1, not to confuse us with the result. So we have Practica 2 with the parameters, and we can add some comments. The INP is the exit output information with geometrical information and rain information. We have also the file INI, initial file, with the different parameters that are generated by default. There are internal parameters included in that file. The RPT file is a result file that we'll be able to open from the path, the notepad. For example, the continuity errors, the summaries of the subcatchment situation, and the summary of node floodings. And we close it, then we will come back. And finally, the Practica DOS.out, where we can store all the information of the mathematical calculation process. It's a summary of the result that we can edit, but in the out, we find everything. It's not only a summary like all the others. Here, for each network element, we can discover its behavior, everything. We get full, complete information, and this is a file that we can read with a specific code. But I think that, and this is something that we can edit, the INI, the INP, very interesting for us. And opening the result file with the free office and with the free office or LibreOffice software, well, we can read those results. So we are opening LibreOffice. To load the RTP file, it's a text file, we first have to check to make sure that the user options are well defined in the LibreOffice, especially the language. especially for points, dots, commas. We need the English typology. So we set it to English language. We go to Setting, Tools, Options, Regional Setting, and we choose English language. And with this customization of the LibreOffice, is it working okay? We open the document. The document will be an RPT document. So we import a text file in a spreadsheet. So we are going to see what are the parameters required to do it immediately. So we use the English language, the Western characters. We will divide it per spaces, and we want to use those two indicators at the same time, to merge, well, those two indicators. We load this file in LibreOffice. So the spaces are the dividers, the borders of those parameters, and it is generating a weird image, but it should be like this. And I can have a look at the structure of the information, all the details about the subcatchment behavior. So it's very well structured, each field in the right place. Now I go to the summary of the flooded nodes, what to know exactly the behavior of my network. We have the summary for surpluses, for floodings. Now I can take those values and I can generate a DBF with them to read them from gvSIG and to link the result with my node table. To generate a DBF, I have to have a header field and the values. As it generates a head field and multiple head fields with different characteristics, I customize the field with a single value. So in the first column, we call it a node. On the first line, I call it, the first row, I call it node. Here we have the maximum flow value. Here, well, the day, the exact day. And here we have the time. For example, well, it happened at 3. And here we have the water that has been expelled, the volume of expelled water in 2 different measures. So to generate a DBF, I need to select those cells, Control C, and Control V to create a new file. So this process is a manual process, it's handmade. I can copy and paste manually, and then I will be able to analyze the result of gvSIG. I can also store the result in gvSIG, and I will get all the information I need in gvSIG without having to go back to other software. We can also include an automatic reading of the files. But right now it's not possible. Then we want LibreOffice to save it as a DBF, for example, Practica DOS.dbf. Again, Western characters. We are running out of time, so I should go even quicker. And that DBF that we have generated, we take it, we go back to gvSIG. I hope that you follow me. I'm creating a new table. The new table is the DBF, the generated DBF. And now, obviously, I have the node identifier of that table. It is the same that the shape node identifier, so I will be able to link that information, like, for example, through import fields. I go to the shape, the node shape. I open the attributes table, import fields, and with the union field under node, my link to, I will link the table Practica 2 with the nodes, and I want to have the information about the volume of water that has been expelled. So I can use the peak flow, or but also the volume that has been expelled to know a bit well the dimension of the catastrophe. I can have all these parameters, so I define exactly well the parameters that I need, the result that I need. And here, unfortunately, I got an error because, well, the table has already cubic meter per second, because as it is the result, the final result of the process, well, at the end, we already had the result if we were not able to get them through here. So it was already set, but we can do it anyway. We are going to do it well. So we put Practica 2, we put node 2, and to cubic meter per second, I put cubic meter second 2. So I rename that field. I put finalize, and unfortunately, I have another error again. Unfortunately, it is failing. Well, I'm sorry. Let's repeat it. So we will exit this table. This is the easiest process, thank God. So we have had no problem with 0 processes, but we are failing here with importing fields. Let's do it again. We will repeat the whole process. Well, you see what I'm doing on the screen. And what really matters is the volume of water that's expelled. It seems that now it is working. I don't know if you are having some troubles too or not. I don't know what's happening exactly. We finish editing. And let's repeat the process again with, well, the same parameter. If it's not working, well, I'm sorry, but this is the last try, the last attempt. It says that it is included. It says that it has it all. So, but I think that the program is a bit tired of me already. Well, the information is included and twice. So, well, you know, things happen. So we have the cubic meter per second. We were not visualizing it before. Now we do. You know, things happen. So, well, I have the expelled volume as a added value in my attributes table. I can put some symbols on my nose in gvSIG with that field, and I can see the information on the screen. I can zoom out to see the network. Finish editing, and I want to see all the symbols per quantity. I choose a classification field. I choose the natural intervals, and we will see, well, the differences according to the format that we want to use to show the results. We will keep the natural intervals, and like, for example, 5 of them. The size, we will choose 15. Well, there is a little trick here that's helping me a lot. We need pix unit. I don't know how you do it. Well, you use that one, pix per second. We request all the other values. They should calculate the intervals. I'll have the symbols per quantities. So now I apply it. Applying those symbols and deactivating the topographic layer and the subcatchment layer too. Well, it now seems very obvious that the main problem happens at that node, the one receiving that extra charge of water. Well, the subcatchment that we have there. So that node, it was the one receiving that inflow, and that we see that high volume of water that has been expelled here and there. You know, those two nodes that we had identified before. So we see very well where the problems are happening, and as an expert, I will have to analyze those two nodes and to try to check possible solutions. We are running out of time. Sorry for going so quick at the end of my presentation. I don't know if you have any question. If not, well, thank you very much for your participation. I don't know if you have any question. I know that the session has been quite intense, quite quick, quite dense, but I hope you have grasped, well, the principle of the presentation. Please use a microphone if you have a question, because we are recording the external subcatchment should also be represented by a node that should be connected. Yes, I have not explained it. Well, it seems obvious, but yes, if we take the subcatchment table, we see that the external nodes have an external code, the subcatchment 01D and 01E, with their corresponding areas. And obviously, you have to explain to which node they are linked. It might be a link with different inflow. The 50 and 34 are receiving their corresponding inflow from the subcatchment around them. So we have a node 34 and 50 with the inflow from the subcatchment 50 and from the external one too. So we could simulate it in a new urban area, for example, to see how this new inflow might have an impact on our system. Well, they have different formulas. You can do it with that, or instead of having a very pervious runoff, we could have an impervious runoff of 0.9, and we are giving a value to that study, and I know exactly, well, the amount given by that subcatchment. Yes, SWMM also allow us to put flows per temporary series, but if another expert has studied this and is giving you other values where we can use those values, not on, and we can use the hydrograms and with those values, and we can really adapt to each and every situation. Any other question in the room? It's very late. We are all very tired. Well, if we have no more questions, then thank you very much for being here, and I hope that it has been useful.